Alright, let's sketch the function f of x is equal to 2x to the power 4 minus 5x, 54x with attention to degree, number of turns, points of extrema, order of roots, intercepts, and domain and range, state intervals of increase and decrease. Okay. So if we're looking at this function f of x, it's equal to 2x to the power 4 minus 54x. What you want to do here is you want to factor it out, right? So if you want to factor it out, you can actually see that there is a common factor. You can factor out, okay, so if I factor out a 2x, you get x cubed minus 27, right? Now, the inside of this, you can actually factor it out further. This is actually, it's a difference of cubes in the form of a cubed minus b cubed. So for a difference of cubes, you can recall that you can factor it as a minus b, a squared, plus ab plus b squared. So if I do that, this basically will become f of x is equal to, I'm going to leave the 2x on the outside, x minus 3, x squared plus 3x plus 9. Okay, so now that we have this is fully factored, what we want to do is assess a few things, right? Let's assess the degree here. So if we're looking at the degree, right, it's a 4, the maximum number of turns you would expect is 3, right? So the number of turns are points of extrema, right? So the maximum number of turns you'd expect is 3. And this degree of 4, also the leading term is 2x to the power 4, right? So this is your leading term. A here is 2, so a is greater than 0. So this tells us that we have a positive even degree function. Okay, so we have a positive even degree function, and if we have a positive even degree function, the end behaviors of that positive even degree function are going to be found in quadrants 2 and quadrants 1. Okay, so that's going to be found in quadrants 2 and 1, and this is going to help us to determine our sketch. Now the next thing we want to do here is find the roots. So let's figure out the x-intercepts. So if we want to find x-intercepts, I'm going to let f of x equals 0. Well, I'm going to look at my factored form, 2x, x minus 3, x squared plus 3x plus 9. Now you actually can't factor this. You can test this by using the discriminant method. It's actually less than 0, right? So your 2x intercepts are 0 and 3. Okay? And after you find the x-intercepts, what you could do is you could find the roots, and you can find the order of the roots. Okay, so in this case, my roots are going to be 0 and 0, and 3 and 0. The order of the roots for 0 and 0 is 1, 3 and 0 is 1. Behavior here, it should pass through both of these points. Okay, so it should pass through both of these points, right? And if we can also find our y-intercept just to keep it consistent. So our y-intercept here, we can let x equal 0. So if we let x equal 0, you're doing f of 0, so you're going to get 0, right? So the y-intercept is also 0 and 0. And now what we can do here is we can determine a sketch, right? So if I want to design a sketch here, okay, so I'm going to design a sketch, and I'm not going to use any kind of scale here. 0 and 0. Let's say that this is our point. 3 and 0. Okay, so this is like 3 and 0. Right? We have a y-intercept, x-intercept, 0 and 0 there. Right? What we can also do here, we know that the end behavior is it's going to end off in quadrants 2, quadrants 1. Right? Well, this tells us that there should be some kind of minimum point here. Okay? So the minimum point here, to determine that, we can just find the turn. Now, because this is a positive even degree function, you should have an absolute minimum. So the range actually gets restricted by this. Now, to find the absolute minimum, what you can do here is there should be a turning point here. X value of the turning point is x1 plus x2 divided by 2, which is 0, plus 3 divided by 2, which is 1.5. Okay? Then I'm going to do is I'm going to plug this in. I'm going to do f of 1.5, and you get 2 times 1.5 power 4 minus 54 times 1.5, and collectively this is going to give us approximately negative 70.875. Okay, so it's a really low point, right? So let's say that this trace goes all the way down. Okay, so it's like somewhere here, negative 70.875, right? And this is your turning point, so this is 1.5 here, right? And that's your minimum point, right? So your absolute minimum, there doesn't seem to be any other maximum here. Your absolute minimum here should be negative 70, let's just write the actual point, 1.5, negative 70.875. Okay, you're probably wondering, well, why is there supposedly 3 turns? We only see 1 turn. Well, what's actually happening is this actually gives you imaginary numbers, right? So whenever you have anything that has imaginary numbers, you're only going to see one turn, right? It's because it actually does a loop, right? So in that sense, because when you do have, and this is kind of like an exception, but whenever you do have an x-intercept, that a series of 2 x-intercepts that are imaginary numbers, then you're not going to actually see the turns, right? So this is your absolute minimum, right? So the domain and range is actually restricted. Well, the range is actually restricted by this absolute minimum. The domain is going to be x belongs to all real numbers, but the range here, y belongs to all real numbers, but y has to be greater or equal to negative 70.875. So this is important, right? That for even degree functions, it does restrict the range. Now state intervals of increase and decrease. Well, if we're looking at intervals of increase, intervals of decrease, I'm going to do interval of increase in red. Right, you can see that it's occurring up here, right? So basically, when x belongs to negative 70.875, it's non-inclusive and positive infinity. Interval of decrease, let's do that in yellow. Interval of decrease, let's do it here, will occur all the way to the absolute minimum, so negative infinity and negative 70.875. So when x belongs to this interval. And that is our assessment of